So have a nice day, everybody. First thing which I want to ask, if you hear me, if you can hear me and see my presentation.
Yes.
Yes is a good start, thank you. Dimitri, could you please copy the link of my presentation to the group chat? Thank you. By the way, one remark, I will, please do not ask the questions from the host during the presentation privately, because I'm the host, and of course I will not be able to really answer via chat. And so let me start the presentation. I will be talking about recent advances of RANSAC, and in them, if I'm able to go to the next slide, I will touch three main topics, and mostly things which were proposed after USAC, or we consider basically USAC as a baseline in this presentation. So USAC contains most of the components, or most of the components were there when proposing USAC, what Ondra just explained to you. And three topics which I would like to touch is the first one, considering methods and the ideas, if it's possible to estimate the models, estimate some geometric models without knowing an inlier-outlier threshold, without setting it manually. And I will talk about three methods, three approaches for this. The first one will be about how to get the model and the threshold adaptively from the data. And then we will be talking about averaging minimal sample models. So in them, we won't even need the knowledge of some inlier-outlier threshold. And also then we will talk about how to use all the possible inlier-outlier thresholds by averaging over a range of them. In the second part of the talk, I will talk about methods which use the spatial coherence of geometric data. We will be using it for local optimization, as Ondra explained, local optimization for improving the accuracy of RANSAC. And then we will talk about sampling, similar methods as PROSEC was in the previous talk. And finally, in the end, I will show I will not go really into depths of multimodal fitting, but I will show the connections of RANSAC-like methods to also to historical multimodal fitting algorithms like sequential RANSAC and multi-RANSAC and such things, and also to the state-of-the-art of multimodal fitting. And to start the problem, first of all, I would say there are two versions of robust estimators without an inlier, without manually set inlier-outlier threshold. So the objective here traditionally is to find the model and find the inliers. And for finding the inliers, we find the threshold as well, with which we can select the points close to the model. And these two problems are, I would say, considered equivalent, since if we have the inliers, I will try to show what I'm talking about with my cursor. I hope you see it. So if we have a set of inliers, then estimating the model is quite easy. With standard estimation problem like least squares, fitting, and such things works quite well. Also, if we have the model, and of course we have the inlier-outlier threshold, since we are looking for the inlier-outlier threshold, we can easily select the inliers which have a residual smaller than this threshold. And in these methods, there is a clear inlier-outlier decision. So in the end, we will know exactly what are considered inliers and what are considered outliers. And we will talk about here two methods, the MinPRAM, the minimum probability random, yeah, I forgot the abbreviation. So minimum probability random sample consensus or something like that. And then we will talk about a contrario RANSAC. The second approach here is what happens if we do not really care about the inliers. So basically what we are doing robust model fitting. We do not necessarily have to know what the inliers are, and therefore we do not have to really make a strict inlier-outlier decision, and therefore we do not really need that inlier-outlier threshold. We just want to find the model. And for this problem, for this version of these robust estimators, we will talk about two or three methods, but two approaches. The first one will be the RANSAC, which will average over a set of minimal sample models, and then we will marginalize, also average out the threshold from the inlier-outlier decision. But let me start with the problem. So this is a standard thing which you have seen also in Yirge's and also in Ondra's talk. then the standard setting is that we have a set of data points. For example, these toy-like scenes with 2D points, and we are looking for a 2D line. And we know the inlier-outlier threshold. This is the blue dashed or dotted, it's dotted line around the red one. And we want to find, so the output are the model parameters. So for example, the 2D line, the red line here, and the set of inliers. But this, not the problem, but the assumption here is that this inlier-outlier threshold relies on or somehow some kind of equivalent to knowing the noise level in the data. So if we have the noise level, we can easily convert it to a threshold, and vice versa. So it is related, the noise level and the threshold. And therefore, for each scene, this threshold should correspond to the actual noise applied to the which contaminates the inliers. But the problem is not that easy. So if we go for example, real-world scenes, here the left two plots are data sets for homography estimation, right two plots are data sets for fundamental matrix estimation, and here each bar shows the model inaccuracy on a particular scene where the model is estimated from carefully and manually selected inlier correspondences. And the thing which you can see here, that all of them are quite different. Even the ranges here are quite different on the vertical axis of the plots. So, and these are carefully selected inliers. So if there is no noise, ideally, this error should be 0, but of course there is noise. And these ranges are quite big. To shade the picture slightly more, it is not the only problem. So of course we can, the source of this model inaccuracy can be caused by the noise in the measured data. And also it's not that easy because it can be it can come from the compression artifacts and such things from the images. But also this model inaccuracy, which we have seen before, can originate from the imperfection of the models we fit. So for example, if we are fitting a standard homography or a fundamental matrix, what happens if there is a rolling shutter in the images? So for example, if you see on the right this helicopter, then you can see in the bottom picture that there is rolling shutter, so the rows of the images are translated, so there is offset. And of course, even if we have noiseless data and we found the perfect model, the residuals, the model residuals will not be 0, and the model will be imperfect. The same thing if we have a small radial distortion, for example, it can be seen here in the bottom images. Even if we fit homography and there is no noise, or if we fit fundamental matrix and there is no noise, the model will be imperfect. Also, again, an example for this problem, what happens if the scene is not completely rigid and we are fitting a fundamental matrix? So a fundamental matrix basically what is a rigid motion in the scene. Usually we consider the background motion as the fundamental matrix which we are looking for. And if the scene is not completely rigid, so for example, it's a face or some non-rigid structure, then the model will be inaccurate, of course. And that is just the imperfection of the models. And there can be other things. For example, we can have an imperfect residual function. For example, when we have epipolar geometry and we are measuring the symmetric epipolar distance, what this means. This means that we have two images. This is the left one, this is the right one. We have the epipolar lines here, the lines which the current fundamental matrix implies. And we measure the point's distance, so x0's distance from the line and x1's distance from the corresponding epipolar line. But the problem here that we do not know if this x0 moves along the line. So maybe we have a 0 residual because it's on the line, but it's at infinity or completely out of the picture. And we cannot measure this because we have an imperfect residual function. Also, other things make setting the threshold unclear. For example, if the image size is different, for example, imagine that we resize the image. In order to get to the same result, we have to resize the threshold accordingly. So it's not that clear how to change the threshold. And also there are problems originating from the nature of perspective projection, such that for far and close objects, we should have different thresholds. For example, if I fit this bottle, I just draw the contour. If I fit this bottle to the image, then this small difference, this I don't know, 5 pixels difference is not that big. I would say a few millimeters in the real world. So a small threshold or quite a big threshold should work quite fine. But if I do the same here for this woman, then it's the same small threshold in terms of pixels, but it's much bigger if we go into real life. So for far and close objects, we should need a different threshold as well. And imagine if there's the Eiffel Tower in the background or the moon or something like that, then even 1 pixel offset could lead to a completely bad estimate. So the conclusion of this few slides is that setting the threshold in RANSAC-like estimators without knowing anything the scene is quite hard. Of course, it can be, we can find quite good thresholds for a particular kind of scenes for structure for motion and something like that, but there is no such threshold which works for everything. Even inside the image, there is no such threshold. And to solve this problem, the mean param algorithm was proposed in 1995. And what it does, so basically the idea here is to find the model and find the threshold together with the model, given some assumptions. The assumptions are that the outliers are uniformly distributed within the sensor range. What this means. So the sensor range, basically you can imagine the sensor range as the image borders. So this is the sensor range. And we assume that the bad points, so the outliers, the points not belonging to that line which we are looking for, are uniformly and randomly and independently distributed in the scene. So this is the assumption. And we are looking for the line and the threshold where the points closer than this threshold. So this is the line, this is the threshold. And we are looking for the threshold line pair where the points closer than the threshold are the least likely to have occurred randomly. And the problem to be, so this is the idea of the algorithm. And the problem which it solves basically is that given a model phi and endpoint, we can calculate the probability of at least k points falls closer than threshold R to the model. Which means that if this probability is, so we can calculate the probability that at least k points falls closer than R to the model if we have random distribution, if we have uniformly random distribution. So this means that if this probability is small, then we likely do not really have a random distribution. There is some structure, there is something which corrupts this assumption about the outliers. So there might be no outliers there, but inliers. And if this probability is high, then this means that that is completely random. That is an outlier model, a bad model, so we can continue searching. And so this is how to select threshold R if we are given a model phi. And the thing which happens, we do exactly the same as RANSAC. So we sample minimal sample models. Then for each sampled model, each estimated model, we get the best threshold R, where this probability, this F is minimal. So the threshold R, where it's least likely happened randomly. And then we simply find the model which has the lowest probability of being random. I have a video showing what really happens. So if we have selected 2 points at random, these red ones here, we fit a model that is the red one, red line here. And what we do, we iterate through the possible set of thresholds. It's finite because all the possible threshold values are basically the absolute residual values of the points, the set of absolute residual values. And therefore, we can easily iterate through all of them. And the thing which we do that for each threshold, we calculate the probability, that is the current probability here up there, of being random, that model and that threshold. And we every time save the minimal. And it stopped, or is it going? I just wanted to show. Okay, it's going. And we every time that the blue line is the current threshold, the green dashed line is the best threshold which we have found so far. And it can be nicely seen how it stops after the probability starts increasing, or before the probability starts increasing again. So this is basically how the algorithm works. And now I can talk about a contrario RANSAC, which basically is a revisiting of the min-prim idea. So we have the same assumptions. We want to find the best model parameters together with the inlier-outlier threshold. And we assume the same things about the outliers as before. So we assume that they are uniformly and independently distributed. There's a background model from which we are looking for some deviations. So the problem is almost exactly the same. The main difference here that we are not looking for the model which has the lowest probability of being happen randomly. We are looking for the model which minimizes the expected number of inconsistent points closer than the threshold, basically. These are called false alarms here. So the problem formalized, this NFA is the number of false alarms, is like we would like to find a model M where this is minimal, this K is the kth closest point to the model, and we start, of course, from M plus 1, because the first M points, if we order the residuals increasingly, the first M points are the minimal sample, and of course the residual of the minimal of all points from the minimal sample will be 0. And then we calculate this number of false alarms, and then we always store the lowest one. So we are looking for the model where the expected number of inconsistent points with the background distribution or with the distribution is minimal. I have a video of that, but it's not that slide. But as I see, I do not say much more in the slide what I haven't said. So let's go to the video. And almost exactly the same thing is visible here as for min-prim. So we have a minimal sample selected at random, at uniformly random here. That is the two red points. We fit a red line to them. Again, we try all the possible thresholds because we know what are the possible thresholds. These are the absolute residual values in an increasing order. And then we calculate every time this current NFA, the number of false alarms, and when it's minimal, the dashed green line stops increasing, and that will be the outputted model. So this is what a contrario RANSAC does. And now I will talk about the random sample aggregated consensus, the RANSAC algorithm, which tries a completely different idea. So the observations motivating RANSAC is that what we have, as we have discussed earlier, setting the inlier-outlier threshold is quite hard. And also, when doing RANSAC, we always do what? We try to find the model with the highest consensus, so the best model. And they claim, they say that by doing this, we ignore potentially useful information. So we ignore all inlier samples, which did not lead to as good model as the best, but they are also good, and we should use all of them instead of just ignoring all of them. And the idea of how to use it is to combine all the generated models, hypotheses, instead of using the best one. And this combination in the paper is done by weighted averaging of the model parameters. But this leads to several issues and questions. For example, what is an average model? Also, how can weighted averaging be robust? What weights are robust, which can be used then to really get a better model than what we had by maximizing? And let me start with the first question. So averaging has to be done in the model. So the requirement of the method is that averaging has to be done in the model parameters domain. This is, by the way, exactly the same idea as what Ondra told you for latent RANSAC. And okay, averaging of translation is easy. Averaging of rotations, rotation matrices, it's quite well known in structure for motion. But averaging affine transformations, projective transformations, such things is not that easy, I would say. And the solution which they propose in the paper is to convert the models to points. So for example, if we have a homography, that is the top row here, then then transform the corners of the images by the estimated homography, and these four 2D points will be then stored. So the 8 coordinates of these 4 points will describe this homography. So these will encode its homography. And of course, we anytime can calculate back the original model because we know that the correspondences. So we know that this corner of the image becomes this, this becomes this, etc. So it can be calculated back. And also we can do this with radial distortion homography, for example, and for a fine transformation and such things. As I see, I have a question on chat. I'm not able, if you ask me privately, I would not answer now. Please ask from everyone, or I can answer in the end. Okay. So the solution is to select anchor points, transform these anchor points by the estimated homography, and keep these points as the descriptor of the homography, and then the averaging is done on the points, which at least makes sense. I mean, we are averaging points in an Euclidean space. It makes more sense than averaging the homography parameters directly. So an example for that, for example, we can have these 2 images. We have correspondences here. Some of them are good, some of them are bad. And we want to find the good homography. And what we do, we generate many minimal sample models, and then project the corners of the models to the image. Now we project it from the right to the left. So we project the image on the left. And then these are the projected corners. I can zoom in here. So you can see that in this group, in the red group, for example, we have these points. The size of the points are the weights assigned to the points. And then we can do something to get back the ground truth, which is shown by a white dot here. So for example, we can do weighted averaging that will here exactly be under the white dot, but here on the bottom right image, it can be seen. We can do weighted geometric median, 2D median. We can do RANSAC. RANSAC means here that we select the point with the highest, with the biggest weight, basically. And after seeing all this, I just realized that I have a zoom in, but I've told everything which I wanted here. But there are some limitations of this approach. First of all, we need to know how to convert a model to a unique set of points. For a homography, I would say the corners of the image might suit in many cases, well, not all cases, but in many cases. But how to convert a fundamental matrix to points, it's not that clear, I would say. Also, it's not always clear how to convert points to a model. So it's clear usually it's clear when estimating from point correspondences, but what happens if we have corresponding lines instead? So we are not able to get back the model from points. And also a limitation that in theory, it requires more than a single all-inlier sample to be drawn to find the source model parameters. What it means, so if I go back, if there's only one all-inlier sample, then there will be only one red dot here. So we cannot do weighted mean, of course. And still, even though it was said that it doesn't need an inlier-outlier threshold, in theory it doesn't. But the weights in the algorithm are set by counting the inliers, and for counting the inliers, we of course need to know the threshold. Also, I would think a bigger problem is that the point to model to point conversion is not really robust. This is what was mentioned by Ondra as well. For example, if we have a homography, we can have problems. For example, we can have this Star Wars scene here, and the corners of the image are transformed to infinity right there, this corner as well, and then the corners will be on the top of each other, and we are not able to calculate back the original homography. Or we are when we know the correspondences, but when we do the averaging, we are not. We will end up with 3 points basically. Also, it won't work if the plane of the homography flips. So this corner goes there, that corner goes there. And of course, when doing the averaging, that corner, the wrong one will be averaged here, and the wrong one will be averaged here. And we will end up with some messy homography, which I would not know what is. And the third approach, which I want to talk about, is basically how to use all possible thresholds. So the idea here is to eliminate the threshold by marginalizing over it. So basically, we are not eliminating the threshold here, but setting it manually, because we are using all the possible thresholds to estimate the homography. And because of this, the model quality does not depend on a single threshold. We do not count the inliers, but we get some probabilities. And also, there is no strict inlier-outlier decision. We, in the end, we will not know what are the inliers, what are the outliers, but we know the model parameters. And of course, if we know the model parameters, somehow the inliers, outliers can also be selected if we have some probabilities and such things. But in many applications, it's not really important. In some, it is, but in many, it is not. And then design choice and data interpretation here, we chose to model the outliers by uniform distribution, and that is a quite usual assumption. And also we assume that the squared inlier residuals model have chi-square distribution, which is, by the way, the case when we calculate the residual as the sum of squared variables, where the variables have Gaussian distribution. So this is typically the reprojection error and such residual functions which we have when estimating the residuals for homography of fundamental matrix. And this, by the way, this instead of Gaussian distribution, this distribution should be used also within RANSAC and within MSAC and such, and in every robust estimator, because that interprets for real the residual function which we are often using. Some likelihood, I would not go into depth of this equation, but I would like to show one thing. So we have some assumptions, outliers being uniformly distributed, inlier residuals having chi-square distribution, and just putting all these things together, doing nothing, just putting all these assumptions together, we can have a likelihood of model theta given some noise level. And again, I will use noise level and threshold as replaceable terms. They are not, but somehow they're kind of equivalent. And yeah. So this is how we calculate the likelihood of model theta given some noise. This part comes from the outliers, this part comes from the inliers. But since we now formalize all the assumptions which we made, we can easily define a new quality function by marginalizing over here the log likelihood function. And what this marginalization means, this basically means that we average over all, we use weighted averaging over all the possible threshold values, all the possible noise levels, and then we calculate this Q star of theta, so the quality of theta, which does not depend on a single inlier threshold, by this weighted averaging over all the possible thresholds. And here, no inlier-outlier decision is made. So we do not know here what is inlier because we do not have a threshold which would help getting them. But there are a few, I would say, problems which are implied by this formulation. First of all, we have no knowledge about the inliers, and therefore we cannot do a final least squares fitting, which is often done, not often, which is always done after RANSAC. And also because we do not know the inlier number, we do not really know when to stop, because the RANSAC termination criteria, as Ondra or Yiri, I can't remember, told you, relies on the inlier number in the data, the inlier ratio. And by the way, a note here that we still have one parameter, this sigma max, that is a very loose upper bound for the threshold, which can be set from a much wider range, for example, an order of magnitude wider than what the threshold was. And for the first problem that we cannot do a final least squares fitting, we propose the sigma consensus algorithm, where the algorithm is the following. So given some initial model, we have a line coming from a minimal sample. So given from two points, so it doesn't really matter how it comes from. But we have some model, and then we can calculate the inlier probabilities of each point marginalized over the threshold, similarly as before. So there's no new thing here compared to the model likelihood when we calculated it as marginalization. But we can simply calculate the probability of point x given some theta. But one important remark here, we are able to replace the integration by the summation, because this integral will be a piecewise constant. So imagine that we have some threshold. We are increasing the threshold, and of course we have discrete points. So we have points. We increase the threshold, a new point comes in, the probability changes, and again we increase, nothing changes, and again a new point comes in, and something changes. And so therefore this integral will be a piecewise constant integral, which can easily be replaced by weighted averaging, by summation. And then in the very end, after we calculated the inlier probabilities of the weights of the points, we can simply apply a weighted least squares fitting, where these probabilities are used as weights. And that is what the sigma consensus algorithm does. The solution for the second problem, that there is no inlier number and therefore we cannot know when to stop, is that we can simply apply the same approach as before. So we have the original RANSAC criterion, where this k is the RANSAC iteration number which was visible from Hirsch's slides, I believe, which requires the model parameters, the noise scale, so that is the inlier threshold basically, and the point set, and it will return us how many iterations have to be made to have some probabilistic guarantees on finding the best model with some confidence value. That is the confidence value. It depends on the inlier number and the sample size, inlier ratio and the sample size. We can do the same thing, so we can marginalize over this iteration number. Basically, we can average over this iteration number and just put this k, so the RANSAC termination criterion, into the integral, and then calculate the marginalized iteration number, and that can be used for if we do not know anything about which points are inliers and which points are not. So the algorithm is as follows. This is one step of the algorithm here shown in the video. The thing which you can see, that we have an initial sample, that is the red dots, that are the red dots there. And we fit the model, that is the red line. And what we do, we progressively increase the threshold. And for each threshold, we select all the inliers closer than the threshold and fit a model by least squares fitting to the inliers, that is the dashed line. This is some temporary model which fits only to the inliers which are selected by the current threshold. And the final inlier model quality are calculated using this temporary model, basically. Some pros and cons. In the tests which we made, it was quite accurate. It has a quite small failure ratio, and setting sigma max is much easier than setting sigma. So setting the maximum threshold can be done from can be chosen from a much wider range than sigma. For example, for fundamental matrix fitting, 10 pixel sigma max, so it still works quite well. Some also 50 pixel and such things will not really mess up the estimation procedure. But in some cases, it can be very time-consuming. I mean, if you go back and have a look on this video, the thing which you see that in every time, for every threshold, we do a least squares fitting, which is time-consuming. Of course, if we find the model early and therefore terminate early, then we solved somehow this thing that being time-consuming. But in many cases, it's not. Also, one thing which is a limitation, and it is not written here, is that it works for only those that models for which we know some way of doing weighted least squares. So we need that for the estimation. And therefore, we propose MaxSec++. This will be shown in this conference, CVPR 2020. I don't know which day, but you can all find a video, I guess. And the idea here is quite similar to the idea of MaxSec. We want to marginalize over the threshold values, over the possible noise scales. But here we assume nothing about the outliers. We do not really care if they are uniformly distributed or have any other distribution. And here we, instead of using some iterative, many least squares and then doing one weighted least squares, we do an efficient iterative weighted least squares approach, which I'm not sure if I have a video. I think for this I do not. But it's basically we proposed a new M estimator here, where in each step of the iterative weighted least squares, we estimate the weights which comes from the from a marginalization procedure, and then we fit a new model using weighted least squares fitting. And same things come here, so we use the probabilities for determining the weights. Okay, so we proposed here a new quality function as well as an M estimator, and that comes as the sum 1 over the sum of losses from the points. But the most important thing here is that we can precisely calculate this quality. In MaxSec, we calculated it approximately, and we can efficiently do it because most of the values here, the properties of the constants and properties of distribution, can be calculated a priori and then stored in a big lookup table, and then we just do a few operations per verification, which is not more time consuming than doing the RANSAC inlier counting, or at least not significantly more time consuming. Okay, so the conclusions of this section is that there seems to have an emerging trend of methods not requiring a single inlier-outlier threshold since USEC was proposed, and three kind of approaches were discussed here. First of all, what happens if we can skip entirely the inlier selection by using minimal sample models? That was RANSAC and VAA. And what happens if we can determine the threshold additively? And also what happens if we would like to use all the possible information from all possible thresholds? And I think I will skip now the questions. I will answer questions in the end of the talk. Because I'm not sure. Yesterday, this talk was 2 hours, so probably it's better to answer it in the end. And also a short note that experiments will be shown in the last talk by Dimitri Mishkin. Therefore, I did not put any experiment here, and also Yerzy and Ondra did not put anything. Experiments will be covered by Dimitri. The next thing which I would like to talk about is ways of exploiting the spatial coherence of geometric data. What it means. So basically in vision, we almost always have geometric data, so data originating from the real world. And in the real world, usually things are spatial, so we have some spatial structure. For example, on the left part of this, on this left, 2 images are rigid motions, so it's toy-like example, but these are rigid motions, so the points are assigned to, the correspondences are assigned to rigid motions in the scenes. And you can see that these are spatially structured, so close points are likely belong to the same rigid motion. Here in these 4 images, you can see the first images of image pairs. So each image is basically the first image of an image pair. And the points are assigned to planes. And you can see that the close points likely belong to the same plane because the plane is spatially structured and spatially coherent. And therefore, its points will be as well. Same thing for LiDAR data. Close points likely belong to the same model. Also, if we do vanishing point detection, maybe the lines are not that close to each other, but if we consider the directions are close to each other. So there is some spatial coherence, at least in the direction domain. And I will be covering 2 methods here. The first one will be a new local optimization step, which uses the spatial coherence to improve the model accuracy. And then I will talk about using the spatial coherence to speed up the estimate, termination by finding models early, basically. So this will be similar as PROSEC, and it will use PROSEC. Okay, so first of all, graph-cut RANSAC. So the idea here is that we should, since the data is almost always spatially coherent when doing geometric model fitting, we can consider this in the local optimization of LO RANSAC. By the way, this LO RANSAC was covered, is the one which Ondra mentioned and explained. And if we could use this spatial coherence in the local optimization, then hopefully we can improve the model parameters. And this can be used, for example, when selecting the inliers of a model. So here you can see an example of rigid motion fitting, basically. So there are two rigid motion in the scene. The second image is up here on the top right corner. This is the first image. And in the left image where the minimal sample, a random minimal sample is selected for rigid motion fitting, and then these are the inliers in the middle, which comes after standard RANSAC-like thresholding. And if we consider that these points, so the points of this rigid motion are lightly structured, we can select more inliers by spreading this inlier. I start with the word label, so this being inlier thing. Through the structure, we can simply select more inliers than what standard thresholding would select. You can imagine this basically as some bumpy threshold, which can be used to reach out from the inlier-outlier threshold, which RANSAC usually needs. So just a short recap what locally optimized RANSAC is. So this was shown by Ondra. This is the main RANSAC loop here, this repeat until loop. There is the sampling when we select the minimal sample. Then we do the model estimation from this minimal sample. Then we do the verification, counting the inliers or calculating some quality function. It doesn't really matter what kind of quality function it is. And then if we find the so far the best model, we store it. And not just we store it, if we find a new so far the best model, we do some local optimization in order to get to the local optima around the estimated model. And this is where the graph-cut RANSAC algorithm comes in. So we propose basically a new local optimization, a new step for this part. The question is how to formalize this, how to exploit the spatial coherence of data in RANSAC. And it's a quite straightforward way to try formalizing RANSAC as a binary labeling problem, because then we can really add new energy terms, including one which considers spatial coherence. And RANSAC is quite easy to be formalized as a binary labeling. So given a set of data points, we have an inlier-outlier threshold, and we also know here the parameters of a model of model theta. And the objective here is to find the labeling where, if the point is inlier, if for pi, so for point pi, if the residual is smaller than the threshold, it's labeled inlier, otherwise it's labeled outlier. So this is quite easy to be formalized as a binary labeling problem. This is exactly what RANSAC does. Just to show the energy which this leads to, is that the problem, we would like to find labeling L prime, which minimizes this 0, 1 energy, where here the possible labels are, of course, 0 and 1. Here the inlier label is 0, and the outlier label is 1. And this is a unary energy, so this means that each term, each part of the, or each step of the summation originates just from one point, basically. So we iterate through all points, and then we measure the loss which it implies, and the loss or the energy which it implies. And energy looks like this. So the energy or the loss is 0 if the label is inlier and the point is closer than the threshold. Also, it is 0 if the label is outlier and the loss and the residual is greater than the threshold. Otherwise it's 1. So there's some penalty on the other cases. This is exactly what RANSAC does. So this is simply a reformulation of the original RANSAC problem. But now we have some beneficial properties. For example, it can be solved in polynomial time, whatever of cost functions we have. It's not true, so not whatever cost functions we have many criteria on this, but if we have a spatial coherence term, that can be solved in polynomial time. And also advantage that new energy terms can be added. And one short remark on this, so it's not necessarily the 0, 1 loss function. We can use any other one. So this is the RANSAC. We can use truncated least squares, maxsac plus loss function, MLSAC loss function. It doesn't really matter. Anything can be used. The next thing is how to put the spatial coherence in the RANSAC algorithm in this labeling. And a straightforward choice would be to go for the Potts model, which is the following. So this binary energy means that it depends on each step of this summation depends on 2 points. This binary energy uses this neighborhood graph. How it uses, so it basically builds on the assumption that close points are likely belong together. So this means that we iterate through the edges of a predefined or pre-calculated neighborhood graph. For example, the corners of this edge is P and Q. And if the label of P and Q is not equal, then we have some energy implied. So we have some penalty for this case, because we assumed that close points are from the same model and therefore they should have the same label. And if this happens, so they have the same label, then there is no energy implied. It's good. We like that, and this is the energy what we minimize. What happens if we use the Potts model for example, line fitting? Here you can see 4 plots of the same scene, same initial. So that blue crosses the minimal sample selected. That dashed line, green dashed line are the lines at the threshold. The green line are the line which we fit. By the way, it is not even an all-in. It is an all-outlier sample. What we used here. This lambda means the weight of the spatial coherence term. If it's 0, then there is no spatial coherence. We just have this. If I go back, we just have this unary term. So that basically is RANSAC. It does exactly what RANSAC does, selects the inliers closer than the threshold. If the lambda is 1, then there is no unary term, there is only the spatial coherence term. Of course, it's not a too useful thing, I would say. But we can observe one thing here, and one quite important thing. So for example, if the lambda is quite high, that is it is the most visible there. For example, 0.9. What happens? So these points are labeled outliers, even though they have quite small residual. And the reason why they are labeled outliers is that we consider outlier and inlier labels similarly in the spatial coherence term. What this means? So there's a big spatial structure here. That is. And there are many points in the spatial structure outside the residual, and therefore most of the points are labeled outliers by the unary term. And that outliers basically spread or force the points close to the line to be labeled outliers because they are in the same outlier structure, because they are in the same structure as most of the other points. And of course, this is not really what we want to achieve when using spatial coherence. The thing which we want to achieve, I would say, is that keep all points which are closer than the threshold, because they are closer than the threshold, they are likely to be inliers because of the unit term, and also try to spread the inlier label outside of the threshold without letting the outliers suppress the good points what we want to keep. And the solution for that, which consider that assumptions and which formalizes that assumption, is as follows. So this is a new energy term for spatial coherence, where we do exactly the same thing. So we iterate through the edges in a neighborhood graph. If the labels of point P and Q neighboring points are different, we have some penalty, some energy. So this is exactly the same. We penalize if the points labels are different, since we assume the same thing, close points likely belong to the same model. If the points, both points are labeled out inlier, so this is the inlier label, then we have no energy implied. That is good, we like it. So if both points are labeled inliers, let's do not penalize it, we like it if we have more inliers, because that maybe is along the structure, it's good. And then if the points are outliers, are labeled outliers, then we calculate the energy which it implies by using some robust losses here from the points. So we penalize if they really are outliers. Otherwise, we penalize slightly less. So it depends on the last loss what the outliers imply. So basically, this says that if they are close to the model and we want to label them outliers, this will be penalized. If they are far, this will not be really penalized. So this is how we keep points which are closer than the threshold to be labeled inliers in the end. And this is what happens if we apply this spatial coherence model to the same scene as before. This works as we expected it. So of course, if lambda is 0, there is no spatial coherence. This is again exactly what RANSAC does. Then we start increasing the lambda. We go for, I don't know, 0.9 just to see what happens. And it can be seen that the points closer than the threshold are nicely kept, and the inlier label is spread along the spatial structure. And this is what we expected here. So we expected to, and here even in this case, even if we started from a quite bad model, so this is orthogonal to what we are looking for, exactly orthogonal, then we can still find almost all the good inliers by simply spreading along the spatial structure. And how this local optimization looks in terms of in algorithmic terms. So this is just the local optimization. It is an iteration. So we do an inner RANSAC, basically. What happens here, in each step, we construct this problem graph and then apply the graph cut to it. So basically, this first part is to get the inliers, which using the spatial coherence assumptions and the unit term as well. Then applying RANSAC. It's quite clear, I would say, why it's required to apply RANSAC. Why it's quite clear. If I go back, if we get these points, and I do a local optimization, for example, a least squares fitting, it will be quite bad because of these points up there. These are outliers for the ground truth model. So if we use the spatial coherence to select the inliers and do a least squares fitting, that will not work. But here, if we do an inner RANSAC on these points, on these red points, it can be seen that the inlier ratio selected by on the points which are selected by the spatial coherence term, is much larger than the inlier ratio on the whole scene. So it's quite beneficial to if we use this inside an inner RANSAC procedure. And again, it's the same as what is done in RANSAC. If we update, if we found a better model, we update, Otherwise, we terminate, and then we give the polished model back to the RANSAC procedure to do whatever it wants with it. So this was basically the idea of putting the spatial coherence in the local optimization step of RANSAC. And the second idea is this is the knapsack algorithm. Second idea is to use the spatial coherence for speeding up the RANSAC procedure by simply finding good samples earlier. Was the basic idea of knapsack that was proposed 18 years ago, basically. Is that the first point is selected at random. You can see an example here. The red one is the first point. And the idea is same what we had in GC RANSAC, is that close points likely belong to the same model. So it's there's a circles, so we get the close points. I cannot follow with my cursor the jumping circle. And in each step, we measure the inlier ratio inside the circle. It can be seen that it's either 0 if the first point is outlier, but if it is not, if it is inlier, then the inlier ratio inside the circle is usually much higher than the inlier ratio in the whole scene. So this is the assumption. If we sample locally, then we likely find all inlier samples. And the algorithm works just as I have shown here. So first point is selected at uniformly random, or it can be by Prozac, for example. And the rest of the sample is selected from this hypersphere, from this circle around the first point. The advantage, as I have said it, as I've told it, is that locally the inlier ratio is higher. There are a number of problems why knapsack, I would say, but correct me in the end if I'm not right. Knapsack is not really used in practice because it has a number of issues which this local sampling implies. For example, localized samples are often imprecise. This is what Ondra said, by the way, when doing the when introducing the degeneracies. But if we select that point in the middle, we get this. For example, this is our circle. I've drawn all the possible lines going through that point and some other from the circle. And it can be seen that even though those are all inlier samples, there's no outlier in the scene, just inliers and noise on them. But none of the lines are really what we are looking for. This one is, I would say, quite close. Some local optimization might help, but all the others are quite far from what we are looking for. And this is because here, if we sample locally, the points are not well conditioned. The conditioning is bad, and therefore the model will be quite sensitive to small changes, even in the data. Also, other problems that for some models, for example, fundamental matrix, local samples will be bad, will lead to degenerate configurations, because for fundamental matrix, the points should originate from more than a single plane. And if we sample locally, we likely get points from a single plane. If we do not sample around the corners, but that is quite unlikely in most of the cases. And also this, and it's quite important in knapsack to set this neighborhood size well, and it is quite sensitive. So for example, if we have this scene, these are just 5 points, nothing more, without noise and without outliers. These are all on the same line with 0 residual if I fit the line. If I did not set the circle's radius, the radius used in knapsack well, then it will never find the good model, even if there's no noise and even if everything is perfect and RANSAC would find it in one iteration, it will never do it. And the thing which we tried to do and we did to solve this problem is in a progressive knapsack algorithm, where the idea is that try to use try to have the benefits of local and global sampling together. So start sampling locally, then try to increase the radius, the neighborhood size, and then eventually we blend into a global sampling. And the idea is similar as knapsack. Hypersphere is assigned to each point, and its radius is increased gradually. So it's not similar in RANSAC in terms that RANSAC had one single hypersphere with a fixed size. Here we have n hyperspheres if we have n points, and each of them is increased according to the sampling frequency, basically. And also we use PROSEC for selecting the first point, and the rest of the sample is selected from the current hypersphere around point P, around the selected point. How it looks: if we selected this first point as the initial one, this red point, the true inliers which we are looking for, the green ones we are looking for that particular line there. And the idea is that we assign this circle, the inlier ratio inside the circle is written here. It will slightly decrease as it gets bigger and bigger, but then we can overcome the problems of localized sampling, because if we do not find a model locally, we do not find a good sample locally, then we increase the neighborhood size, and eventually we will find it, or we will end up with a simple RANSAC or PROSEC scoring when the circle covers the whole image. So we tried here to combine this property that small circles have high inlier ratio but poorly conditioned, and big circles are usually well conditioned but with low inlier ratio. And the conclusions of this section is that exploiting spatial coherence is beneficial both in terms of accuracy by using it in local optimization, or also for improving or speeding up the procedure by finding good samples early. And one message, or one thing which I think is important, so these things are just components of RANSAC. So I mean, if we are talking about progressive knapsack sampler, it can easily be, and it is combined with PROSEC sampling. So we do not have to choose one thing. We do not have to choose to use the spatial coherence and then nothing else. We can combine all of these things, and then in the experimental section done by Dmitry Mishkin, there will be combinations of such methods which lead to quite good results. For example, combining GC RANSAC with MACSAC scoring and such things. Okay, I will go for the questions here again in the end. I think now I will have time. I'm speaking quite fast, so I hope you understand, but I will finish in time. So the last thing which I would like to talk about, not really in depth, but to give some intuition about the problem, is the multimodal fitting with RANSAC-like methods. And I would say I could remove the with RANSAC-like methods from the title, because multimodal fitting, even recent and historical multimodal fitting, always relies on RANSAC-like methods. And the problem here is that, as Jerzy have told it in his presentation, we can have multi-instance and multi-class. I will not care about it now. We have a set of models, three planes, 2 planes, and a cylinder, and 3D rigid motions, different kinds of rigid motions, non-rigid motions. We have some models. I do not care about the class, but the main thing is that we have more of them. And we are looking for a set of models, interpreting the scene, interpreting the data points, and also we would like to determine a point to model assignment. So basically we want to say that that particular point from the data belongs to that plane. So this is done in RANSAC as well, but here again it's important that in the end we want to know what points belong to what models. A short note, of course this can also be formalized as in MACSAC. So I would say it's not really necessary to have to point to model assignment, but in a standard setting it is. I will talk about 2 kinds of methods. The first one will be the early methods, which we're using directly RANSAC to get the final model parameters. And then I will talk recent and state-of-the-art algorithms, which either use RANSAC as an initialization and then do something, or use RANSAC inside the optimization, inside the main optimization, not as an initialization, but as a main step of the algorithm. So one of the earliest methods for multimodal fitting is the sequential RANSAC algorithm, and it is quite easy to imagine what happens here. So we are looking for these two lines. We have a set of data points, and what we do, we apply RANSAC. We get this blue line. Then we remove the inliers of this blue line from the data, and again apply RANSAC, and then we get this red line. And then we stop after a while. And even though it's a greedy algorithm and it cannot really solve complex scenes, it works reasonably well for finding the most dominant models. So, I myself quite like this algorithm because it's quite easy to implement and it's scalable, and that is not necessarily true for most of the state-of-the-art techniques. And therefore, I think sequential RANSAC is still widely used in many cases. So I still see some papers in conferences which use sequential RANSAC to get multiple models or something. The second algorithm is the multi-RANSAC algorithm. It was proposed 15 years ago. And what happens here? So for multi-RANSAC, we need to know how many models we are looking for. So K, the number of models, is a parameter of the algorithm. And what we do, we basically apply RANSAC, nothing more. But instead of, in each iteration of RANSAC, instead of selecting a minimal sample, we select K minimal samples. So this can be seen here. In each iteration, we select randomly, at random, the minimal samples of all K lines here. And then we return the configuration which has the maximum total inlier number, so the sum of all points which are closer to one line at least, basically, the number of points which are closer to one line. The idea is clear. We can have some probabilistic guarantees which RANSAC had, but there are a quite big problem with this. So as Ondra said, the iteration numbers to get that probabilistic guarantees, it depends on two things, basically. It depends on the outlier ratio in the data and depends on the sample size. So for example, if we fit a line that requires 2 points to be sampled at random, and for example, we have 90% outliers or 75% of outliers, we have to do 71 or almost 500 iterations. It's doable, I would say. But if we have to draw samples of size K times or 3 times 2, that is 6, that is 2 orders of magnitude, 3 orders of magnitude increment in the iteration number. And still, it is just 3 lines, and the line is, I would say, one of the least complex models which I can imagine. Imagine trying to fit 5 fundamental matrices, where fundamental matrix requires 7-point correspondences to be estimated, and to being able to estimate it, and then 5 times 7. I would say I would not go for it in practice. So it's not really a practical application. But the idea is clear. And these were the historical algorithms for returning multiple models from using RANSAC. And there are some recent methods, and there's a connection between almost all the recent state-of-the-art multimodal fitting algorithms, is that they use RANSAC as an initialization. What they do, they get the data. They generate many, for example, thousands or hundreds or 10,000s random models by a RANSAC-like procedure. They have many, many hypotheses, many models, and then they do something. This something can be many things. There are energy minimization-based approaches, this Pearl algorithm, I hope I put it there, I wanted, of boycott, I did not put it there. Doesn't matter. So energy minimization based approaches. There are preference analysis based approaches. So, and there are also hypergraph segmentation, where the hypergraph edges are basically the models going through their inliers. So there are many kinds of optimization techniques, and in the end we will get the final model parameters. I would say, to my experience, the problem of these methods is that in the very beginning they lose the efficiency. So as soon as we generate a bunch of models, many models, we have to go for the worst case scenario, because to have some probabilistic guarantees of really finding something. And if we go for the worst case scenario, so we assume that, I don't know, the inlier ratio is 0.1 or some very small value, we generate thousands of instances, and then optimizing thousands of model instances, hypotheses, are quite time sensitive, are quite slow. Also, we can choose not to go for the worst case scenario, then we do not have any guarantees of really finding what we are looking for, and we will miss most of the dominant models. And some recent methods, this was proposed last ICCV. This is the progressive X algorithm. A short note that there is also a similar approach proposed in this CVPR, that is the RANSAC algorithm, which uses some kind of similar strategy, but by using deep learning for proposing models. And the idea here is that we know that sequential RANSAC will not work because it's a greedy algorithm, but we also know that generating a bunch of model instances at the very beginning and then trying to get rid of them, rid of the bad ones, will not work either, because then we lost the efficiency and we can never be really fast. And the idea of that algorithm is that we have a set of input data points. We have some pipeline which tries to mix this greedy approach of sequential proposal and the global approach of optimizing all models and everything together. And the thing which it does, with each iteration, this proposal engine proposes a new instance, a new putative instance. This is then verified just by quick verification using min hash and some Jacquard distance. It's not that important at this point, just to quickly decide if it's worth the time to be verified or optimized together with all the capped model instances. If it does not, then let's do early rejection, go back and let's propose a new model. And then if it survives this rejection, we go for optimization. And this optimization means that we reassign, we always have a compound model, which basically a set of capped model instances. And we try to insert this new line into this compound model by reassigning the points, maintaining the previous model parameters, maybe deleting, destroying some of them, and so things can die here as well. And this is where the optimization part comes in, that we always do the optimization on just a few models. So this is here in the algorithm was some energy minimization based approach, Perl, but it can be anything else. But the main property here, that it's always done not on thousands of model instances, but always on a few. So it's quite fast here. And then we again go back and propose a new one, and it's repeated until the data, the most parts of the data are interpreted. And in the end, we hopefully find some good thing. I have some videos which were shown by Jerzy as well. I will go slightly deeper in explaining the videos, because these are connected to these are done basically by this progressive X approach. What happens here, by the way, a short remark, if I go back to this proposal engine was GC RANSAC in the original paper, but it can be anything else. It can be DEGANSAC proposal, which Ondra mentioned. It can be MAXSAC or anything else. It doesn't really matter. The idea is here, we propose something and then try to explain it given the data and given the previously proposed models. So the thing which you can see here, if I start a video, so this is on the left side, I maybe go here and tell what you see. So these are two pictures, the same scene, but two pictures. This is the proposal, the current proposal in the first iteration. The blue points are inliers of the proposal, points which are close to the proposal. We do not see green and red points yet. And then what we do, we try to optimize, insert it into the compound model. That is easy because that is the first model. Then what we do, we have a new proposal. We keep the inliers of the compound model. We try in the proposal step, we try to propose models which haven't seen yet. So which have the minimal number of red points here, where the red points are the intersection, the points which are close to both the compound models, so the maintained model instances, and also the proposal. So we proposed a new one. It was inserted. We again proposed a new one. We again propose here, and this is what happens. We apply in each proposal step a RANSAC, which has a slightly modified scoring function in order to count or use only those points which are not shared with the compound instance. And then with this guidance, it's quite easily finds the good model. And each iteration basically is a good model. On the right, you can see the compound instance. So all the kept and maintained model instances. If you look carefully, you can see that in each iteration, the lines slightly move when some points are reassigned, and then they are refit to, the lines are refit to the models. I can come here as well. So this is homography fitting. Each column is a image pair. So this is the proposal. The left two images, the right two images are the compound model. And what happens here? We propose the homography, which has these inliers. So this plane, basically, you all can imagine this plane, and that is then inserted. Those are the pink points. I hope it's visible. And again, we propose this blue one. These red ones are its inliers. The green ones are already assigned to some model in the compound model, this one. So those are the green points. We get this, we get that, and those are all assigned. The interesting thing here, now I go back. Okay, so the interesting thing here the algorithm tried to again propose the same model, but nothing changes because those points are almost the same as something which we already have. So the early rejection kills it, basically. And also this is interesting because here the homography, or the plane which interprets the homography, cuts through the walls and goes like this. And of course nothing changes because the optimization kills this, or do not insert it. And then after some iterations, hopefully that wall here will be found, and it's here. And so the conclusions of this section, and of course everything, is that there are still a number of problems of robust model fitting, and one of them is how to set the threshold in a way that it can interpret more scenes and can be used more generally without really a manual intervention of setting it. And also the take-home message I would say is that we have geometric data. This data is almost always spatial coherent. We should use this spatial coherency in order to speed up or improve the accuracy of the algorithms. Okay, so that was all. Thank you for your attention. And now this is the time for questions, I would think. We have 11 minutes for the questions. Okay, and I do see now questions in the one question in contrario, and it's like, what happens if random stuff is not a good model? Okay, so Yeji answered to it. If you have any other questions, I'm here waiting just for you to ask those questions. I had a question privately before from Monir. So one question, MinPran, what is the cost of calculating the optimal R using both MinPran and Alcantara or RANSAC? In terms of time, there's no big difference. I would say both of them are just a few calculations. I think Alcantara and RANSAC is slightly more calculations, so not 10, but 20 or something like that, but not significant. It's not a significant difference. Okay, I think I turn off my camera so I can drink my energy drink, and I still see the. Oh, I have a question. What methods would you recommend for close or to real-time estimation of planes in an indoor scene? You mean multiple? When you go for multiple planes or just one plane? Multiple, yes. At the first attempt, I would go for sequential RANSAC. Then at the second attempt, I would go for something similar if you want to go for real time. For example, you could try Progressive X that has implementation on GitHub. Because that was also proposed, that was also quite fast in such tasks. But yeah, so if I were you, I would first try using sequential RANSAC. That will work quite fine if the scenes are not that complex and we are talking about just a few dominant planes. Can the discussed methods be integrated into deep neural network framework? Yes. I mean, I don't. So they can be combined. I'm not sure about being integrated. What this means. I'm not an expert on the deep neural networks, but you will hear combinations in the experimental section where we combine MaxSac or GC-RANSAC with some networks providing the some initial labeling, and that will be shown. Yes, by the way, all the presentations and all the record, so the whole video will be available and all the presentations on our website, which Dimitri will soon copy there, or I will copy there. Okay, if there's no more questions, I turn off my camera. I'm still here, so I can answer. And I think we'll have a longer break now. Let me check what was the planned program. Okay, yeah, so there will be a 1 hour break now. This was supposed to be have lunch or something like that. For most of us, I would think it will not be lunch since it's evening here. So, but it's a 1 hour break. And then there will be Tachin Chin presentation about mathematical programming approaches and such things. And then René Ramp will talk about the latest development using differentiable approaches for robust estimation. And these all things will be then experimentally validated on quite a number of problems. I mean, fundamental matrix essential and homography and such things by Dimitri Mishkin, including deep learning approaches and including their combinations with the things which we have just discussed. Oh, I have a, what is the question? Okay, do you know a RANSAC paper that make use of curved arcs and elliptic segments and identifying corners in the sections? Honestly, I do not know. Maybe there is. Maybe usually have read something like that. And if yes, then he will answer. But by the way, regarding this segments and using segments to identify corners and such things, I read a paper with which were doing hierarchical multimodal fitting, which first detected, I think, homographies and the fundamental matrix on top of them. I can easily imagine such case when you, for example, first detect some curves or lines, and then on the top of these lines, you detect some more complex model, or even in the opposite direction. I will find that paper and will copy. But usually already answered, so it's good. So what is quadrilateral shape? You fit 4 lines, and so I would probably go for multimodal fitting to find 4 lines instead of you can fit 4 lines as it is done in MAXSAC, not MAXSAC, sorry, in multi-RANSAC, but as we discussed, it won't really work. But you can find multiple lines and then try to cluster them into. I'm not sure where I'm going in the. So that is. So the question is if there are any RANSAC which take the confidences into account, like what if one is the homographies. So basically, I would think that is a problem for PROSEC, where you have some confidence, you know something about the data, you know some ordering of the points according to their quality, and then you can easily use PROSEC and speed up the procedure, speed up finding the good model by simply using these confidences as some quality measures for the points.
So, can I use voice to ask a question?
Yeah.
So that would affect the sampling, right? But that doesn't actually affect the definition of an inlier or an outlier. Are there any?
Right.
So is there any way you can like weight the inliers or outliers based on the confidence? Because if I have a low confidence inlier, I don't care about it as much, right? Is there anything like that you know of?
I have ideas, of course. So you can build some probability on the top of it or something like that. But in RANSAC, this decision of being inlier and outlier depends on the threshold. You can of course put together things and do some makes the called loss function to use the confidences, but I'm not sure if that would work.
Okay, yeah, no,
but maybe yeah. By the way, it's true what you just said. So you can use the confidences in some deep networks, and Rene will talk about it.
But also there's this thing like the confidence, which is like a priori, and then given the residual. So we have at least 2 pieces of information. A priori, given some comparison, I have some confidence, and then I have the residual. Should be combined. It's not like the confidence in a certain point is unchanged. If
Okay, that makes sense. So I will read the. Is there any particular paper? I guess I'll wait for Renee's talk. That'll probably be good.
We are happy then.
Yeah, I think one of the stories with the deep nets, which are end to end, is that they try to estimate something like confidence. And now the question is whether we call it a confidence or weight. Doesn't matter, because if we say confidence, it can have many interpretations. And it turns out that if you get these numbers which are low for things likely to be outliers and high for things which are likely to be inliers, it turns out this weighted iterated least squares have quite large area of convergence. And of course, these weights change as you improve your model, because things which are sort of inconsistent, their weights drop and so on. So, but the results in the benchmark, which will come very late, suggest that the best is to combine both worlds. Yeah, so use the weights and use sampling together. That will be one of the messages from Metro's evaluation.
Thank you. Yeah, that makes a lot of sense.
Okay, so if there is no other question, I stop my screen sharing. And I think we will still be reading the chat window if you have any other question. Otherwise, we will come back in an hour with Renee's talk or TJ's talk. Maybe it's TJ's talk. Let me check. So yeah, with TJ's talk about mathematical programming and such things for robust estimation. Thank you. Yeah, and by the way, this will be this meeting will be kept alive. So this will be the one when you